Hello everyone, we have discussed calculus of variations last class. We have reviewed the concept as well as some of the fundamental theorems and all that, primarily Euler-Lagrange equations associated with boundary conditions, things like that. Now, using those concepts we will be able to formulate optimal control problems and we will see the applications and rather directly here actually. Okay, so, this particular lecture will talk about optimal control formulation using calculus of variations ideas basically. So, the topics to be covered in this lecture is something like this. First, we will have an idea of what is an optimal control problem, what do you mean by that, and what is the objective of this particular formulation, and how do you select this performance index actually, that is which is a critical component actually. And then how it leads to this 2-point boundary value problem formulation, I mean that is important thing because that is the most critical point in why these problems are computationally difficult in general. Then we will also have some associated boundary and transversality conditions followed by numerical examples actually. So, let us see what this optimal control formulation means, what is the objective and how do you select this performance index and things like that. So, the objective in a nutshell is something like this, we need to find an admissible time history of the control variable ut from t0 to tf, okay, which satisfies all these conditions number 1, 2, 3 and one is the first condition is it needs to satisfy the system dynamics, that means this control history u should cause the system governed by this differential equation which is essentially the system dynamics to follow an admissible trajectory. Okay. And while it does that, it also needs to optimize certain cost function and that has to be meaningful actually. And many times it is called as performance index, some people call it as cost function also basically. Okay. So, either we want to minimize it or maximize it while finding out this admissible trajectory, we need to also keep in mind that this cost function needs to be optimized. Associated with it needs to satisfy certain boundary conditions and the boundary condition in our case is initial condition is like this, like t equal to t0, your initial condition is x0 which is specified and at t equal to tf xf is typically free and we will consider rather tf is fixed. Remember that these boundary conditions sense many things can be flexible out here, I mean in other words x0 need not be fixed, tf need not be fixed, you can have see essentially we have t0 x0 and tf xf combination actually. So, any such combination should do the job and here we will typically interested in this type of a condition because this is practically more relevant actually. We also see that the typical form of the cost function that we take here is also kind of practically relevant for many example problems actually, we will see that next actually. So, without I mean if you see this cost function, if this is this entire formulation, this state equation or the system dynamic equation is something that is given to us, we do not have too much of choice in that, but while formulating the problem number 2 and 3 will typically play a role and in this lecture we are fixing 3 also, that means we are interested in this particular case where t0 is fixed and initial condition x0 is also fixed, tf is also fixed, the only thing that is free is xf actually. Okay. X at tf. So, but still we have the flexibility or freedom of selecting this in a meaningful way. How do we select that? So, let us give some intuitive examples which will make our ideas clear. So, let us say you want to minimize like the operational time actually. So, this is some particular application we are interested in minimization of operational time. That means, we want to minimize this tf minus t0, okay, which essentially I can write it that way, integral t0 to tf1 dt. So, if you go back and see, then this phi in this context turns out to be 0 and in L turns out to be 1. Okay. Similarly, if you want to have minimum control effort, that minimize the control effort, then essentially we want to minimize this kind of a cost function where R is a positive definite matrix. Remember this is like a quadratic cost function, that means we are minimizing this something like half of r1 u1 square plus r2 ut square plus r3 u3 square like that actually. If you take R as diagonal matrix, which most of the time this R is taken as diagonal matrix anyway. Okay. So, to minimize the control effort, we want to minimize such a quadratic term. Okay. And similarly, if you that means if you select this cost function that way, then if you again go back, then phi turns out to be 0 and L turns out to be this one, okay, half of U transpose R U. Similarly, if you want to have a different problem where you essentially want to minimize the deviation of state from a fixed value C with minimum control effort, as is typically you can relate this to like let us say helicopter hovering. That means the helicopter needs to stay at a fixed position C, with that needs to be done with a minimum control effort. Then you know the position C. So, essentially you want to formulate a cost function that way, where you can talk about okay, the deviation of x from C needs to be minimum actually. So, that means I need to have this quadratic term for that particular job as and this particular term makes sure that we have minimum control effort also basically. And whenever you see these quadratic terms containing a state and control, typically the conditions like conditions pop up are like Q has to be positive semi-definite matrix and R has to be positive definite matrix. But that aside, if you go back to this this particular cost function form, then obviously in this case also phi is 0, okay, as well as this L turns out to be everything inside that with half actually. Okay. Now, another one, suppose you can talk about minimum of deviation from state, I mean minimize the deviation of state from origin with minimum control effort, like a kind of a special case for this, and this is essentially the regulator problem. Okay. So, later we will see that this linear quadratic regulator all typically assume this such a cost function actually, and here also again phi is 0 and L is this entire thing including half actually. Okay. So, that is that kind of a thing. Suppose we want to okay, another problem where you do not want this path dependent control, I mean minimization of state, but we want to minimize the state at the end. When t equal to T f, we want to minimize the state. Okay. On the way we do not care as long as the control is minimum. So, then we know the at t equal to T f the let us say like aerospace vehicle, then you can think about something like position of the destination airport basically probably. So, if you really want that T 0 to T f at t equal to T f, then your position of the aircraft from the destination airport should be as minimum as possible that way. So, then this turns out to be phi, okay, in this situation because it is outside the integral, and L is half of that actually. If you correlate to this is anything that is outside is T f dependent, the final time dependent, anything that is inside is the path dependent T 0 to T f actually. So, again in this situation, okay, this turns out to be phi and this turns out to be L actually. Okay. Now, optimal control using calculus of variation, that is that's Hamiltonian formulation. So, that is I mean these are all these examples has given us some idea that this cost function that we are discussing here has sufficient generality to talk many different class of problems. However, also remember that this is not the exhaustive set actually. You can even think beyond this particular form of cost function, and that is certainly valid as long as it admits a solution actually. So, those things will not discuss in this lecture. Alright, so let us go back and see how do you use this calculus of variation ideas and things like that to come up with some solutions to this class of problems actually. Remember, when you talk about optimal control formulation, depending on the problem you need to select j nobody is giving us j, we need to select ourselves, and phi also, I mean this phi L all sort of thing, as long as I mean along with boundary conditions and everything we need to formulate it properly. But once you formulate it properly, then the solution procedure and all, how do you find out? I mean that's the thing that we are going to talk next actually. Okay. So, let us see, let us go to that and then tell okay, optimal control problem is something like this. Okay. We want to minimize or maximize a certain performance index or cost function which is of this form, subject to this path constraint which is system dynamic equation x dot equal to this for TXU non-linear systems in general, and the boundary conditions needs to be kind of well formulated. So, for example, here we are talking about T 0 is fixed at 0 and x of 0 is x 0 which is also specified, T f is fixed, x of T f is free actually. Okay. So, how do you do that? Now, if you remember this static optimization and all, whenever you have a equality constraint, we actually had something like a augmented performance index j bar with which is like lambda transpose times this I mean this f of t x u minus x dot equal to 0 that way. Okay. Now, here also we will proceed with the similar idea, but here we will tell okay, this is a path constraint which is valid from t 0 to t f everywhere. So, this path constraint, this augmented cost function j bar needs to have this particular term inside the integral actually. So, that is what we are doing here. Okay. And for the sake of simplicity I am dropping out this arguments and all that actually. So, j bar is nothing but phi plus L plus this lambda transpose times f minus x dot. Remember f minus x dot is equal to 0, that is the path constraint actually. So, that has gone there actually. Okay. Now, for further simplicity what you do here is this derivative independent term what you see here L plus lambda transpose f is actually independent of derivative. So, we will just define that as Hamiltonian, this is standard definition which helps us in algebra simplicity basically. And whatever is derivative dependent we will leave it as it is actually. Okay. So, essentially j bar is nothing but phi plus integral t 0 to t f then h minus lambda transpose x dot actually. Okay. And hence, the first variation of that will turn out to be like this. This variations and all remember these are like linear operators satisfy that definition. So, this variation of j bar is variation of phi plus variation of this one. And now, remember there is the theorem in the calculus of variations where it talks about variation of integral is integral of variation. Okay. So, we will using that we will be able to take this variation inside the integral, and then again this this variation of this particular term will take advantage of this linear operator property of this variation. So, this is del phi plus integral t 0 to t f variation of all this term, where you will expand this like linear terms and all that actually, I mean like variation being linear operator like that. So, let us expand that inside the bracket and then tell okay, there is a first the first variation of h minus the first variation of this quantity, and again this first variation of multiplication will satisfy this derivative sort of property there, and using that we will be able to expand that actually. Okay. So, this is the first variation of del j bar is nothing but del phi okay, plus integral this del h. So, we will keep this term as it is okay, minus del lambda times x dot minus lambda transpose times del x dot. So, that is coming from this very first variation of this expanded form actually. Okay. This is what we have. Now, let us analyze this term individually, term by term sort of expansion and all that. So, now see del phi for example. So, phi is a function of t f x f, and remember this we are talking about t f is fixed. So, there is no variation on t f as such actually. So, the variation of phi comes through the variation of x f only basically. So, and hence this first variation of del phi turns out to be like this okay, del x f transpose times del phi by del x f, and the first variation of del h okay, is something like so remember h is a function of t x u lambda everything basically, because h is nothing but L plus lambda transpose f. L and lambda are function, L is t x u lambda, I mean this lambda is a function of time, and then it is a function of everything actually. So, first variation of h will come from variations of x, u and lambda. Remember time is an independent quantity. In calculus of variation we have the flexibility of starting somewhere we want and then stopping somewhere we want. In other words, t 0 and t f can have some variation, but on the way once you fix the t 0 and t f there is no variation on t, this is an independent quantity actually. So, because of that this first variation of Hamiltonian takes this form actually. So, we will consider that as variations coming from variation of x, and variation coming from variation of u, and variation coming from variation of lambda, and hence this expression this expansion holds good actually. Now, what about the next term actually? Now, next terms contain remember these are like derivative terms and all, and this particular term we will keep as it is okay. But this particular term talks about something like variation of derivative. So, which is not kind of so much comfortable. So, let us try to examine that, and we will examine in the context of integral directly, because ultimately we want to put integral back actually. So, this integral this lambda transpose del x dot, that is what we want to analyze, and by definition this is dy dt of dx, because variation of x dot is dy dt of variation of x, and then we excite that I mean this integral by parts actually. So, this is the first function, that is the second function, we put that integral by parts, and hence this first term is something like this evaluated at these values t0 and del x0 and tf del xf minus the derivative of first term into the integral of second actually. So, that way it turns out to be like that actually, and hence if you put them together, okay, this turns out to be like lambda transpose lambda f transpose del xf minus lambda 0 transpose del x0, this particular term. But remember this there is no variation of x0, we are interested in only fixed initial condition cases. So, obviously this goes to 0 actually, okay. And hence I mean they are left out with only this term, and because of that we in a simplified way we can write it that way actually, okay. Remember you can we have exchanged this term, okay, this to that, and this is primarily because whenever you have a two vectors multiplying each other of the same dimension, one is row and one is column, so that the product is scalar, then the multiplication is interchangeable. In other words, x transpose y is equal to y transpose x, because both are the same quantity, which is nothing but like x1 y1 plus x2 y2 like that, which is equal to y1 x1 plus y2 x2 like that actually. So, because of that this x transpose y is equal to y transpose x, and that is what we have done here actually, because they are two vectors of same dimension, multiplication of that both the vectors is ultimately a scalar. So, taken advantage of that here. Now, we are ready with all these terms, because this is something we do not want to do anything, we just leave it. This is something we have expanded, this is something we have expanded, and this integral sense also we have expanded. So, let us go back and try to put everything and then try to see what this delta j bar takes actually. So, if you do that, this then delta j bar takes that form, okay. So, first term is coming because of that this term. So, we just keep it that way, okay, minus this del x I mean del x f transpose is because of that, because remember ultimately this is a minus term here. So, we have this sign change will happen here, this is minus term coming here, which is like that. Again we can extend this quantity, because these are again same two vectors of same dimension, and ultimately the product is a scalar. So, we can extend that and write it that way. And the other terms we just keep it that this is first variation of del h, okay, this one, okay. So, this term is nothing but that. So, we keep it there whatever we have, and then the other term is like that, okay, and the left out term is like that actually. Remember this term will become positive later, I mean because of the sign change and all. So, once you put that together, okay, all these things, and then try to combine terms as much as possible. For example, I have del x f transpose here and del x f transpose here, and both are acting to the left actually. So, I have a liberty of taking common to each other. So, I mean just I take that common. Similarly, if you see all these terms are integral quantities, all are of the same integration limits t0 to tf. So, I can put one integral in I mean I can combine terms within that as well. For example, if I see these two terms, this del x transpose is multiplying to the left. So, I can combine these two terms, and similarly this is del lambda transpose appearing to the left. So, I can combine these two terms. So, that is what I am doing here. I have combined this all the terms pair. Only thing that is left out is this one, because that del u transpose acts only here actually, okay. Now, because of this I mean ultimately we are left out with this, and remember the one principle of this optimization necessary condition from calculus of variation is the first variation of del j bar, that is delta j bar, needs to be equal to 0. So, that is what we want ultimately, okay. And then if this condition happens for all sorts of variations, that is another theorem that we outlined last lecture. We talks about if it happens to be 0 for all possible variations, then the only way that it can happen is the coefficients needs to be 0 actually, okay. So, because of that we collect coefficients, various coefficients whatever happens here, and then we put them together and make it equal to 0 here. For example, this coefficient has to be equal to 0, this coefficient has to be equal to 0, this one has to be 0, this one has to be 0, like that. So, once you do that, the first equation pops up is something here, x dot is del s by del lambda, and del s, and then if you go back to the H definition, del s by del lambda is nothing but simply f actually. So, that is what we are trying to see here. So, x dot is del s by del lambda, which is nothing but f. So, that is f, and x dot is f of t x u is nothing but the same state equation that we started with. So, the system dynamic equation or state equation becomes part of the necessary condition actually, that automatically happens that way. And then the co-state equation will pop up from this one. So, this coefficient if you make it equal to 0, then lambda dot equal to minus del s by del x. So, that is what happens here. And then the optimal control equations, there is nothing, del u transpose is only appearing here. So, del s by del u has to be equal to 0, and in the boundary condition sense we have this term equal to 0. So, lambda f is del phi by del x f actually. Okay. And obviously, x of t 0 is x 0, which is known to us fixed. So, what is happening here? If you see these quantities, okay, there are a couple of things to observe. First of all these conditions are necessary conditions, because they use first variation only, second variations and all we have never explored actually. So, it can happen to be either maximum or minimum if you satisfy all these equations, but from the nature of the cost function that we select, we can tell okay, it is either a minimization or maximization problem intuitively actually, okay, because cost function is something that we are selecting. So, that way we do not need too much of further mathematical testing and all, we can intuitively it can have only minimum or it can have only maximum, then one is good enough anyway. So, that is how we use these results for engineering problems actually. Now, second point, we have a bunch of equations here, okay, and if any one of these equations is not satisfied, okay, then the entire solution is non-optimal, okay, and the solution can be very far away from optimal solution also actually. So, just by changing the boundary condition for example, okay, we can have a very different solution from by putting another boundary condition that way. So, just make sure that all these conditions are satisfied. If one is left out, then the entire solution is non-optimal actually. Okay, third point, if you see this x and lambda, the dimension of x and lambda turns out to be same, because Hamiltonian is a scalar quantity, del s by del x will give you the same dimensional vector as x actually. So, lambda and x are of same quantity, lambda and x are of same dimension. In other words, this is also n by 1 and x is also n by 1. So, essentially to solve an n by 1 problem, we have to actually solve this 2n by 1 dimensional problem through lambda actually, using lambda basically. Okay. Okay. Now, if you also remember, observe these equations carefully, the first two equations are actually dynamic equations that contains a derivative term, but the third equation is actually a static equation, there is algebraic equation actually, where all these three equations are valid from t 0 to t f everywhere actually. Okay. So, from t 0 to t f you satisfy all these equations, out of which two are dynamic equation and one is static equation. In the boundary condition sense, that is the most difficult thing by the way. It turns out to be that part of the initial condition, part of the conditions are given at t 0, which is initial condition, and but part of the conditions are given at t f, which is final condition. Remember, the entire problem lies with two particular variables, x and lambda and 2n plus 2n by 1 dimension actually. Okay. Out of these 2n variables, n variables are given at t 0 and n variables are given at t f really. Okay. And because of which this excites the condition what is called as 2-point boundary value problem, and hence it is difficult to solve also, because you cannot directly use this numerical integration techniques to propagate these equations either in forward in time or in backward in time. So, you have to do this back and forth calculation several times repeatedly in an iterative sense to get the solution actually. Okay. So, all these points are summarized here. Okay. So, first thing to notice, state and co-state equations are dynamic equations. Optimal control equation, which is this equation, sometimes it is also called a stationary equation by the way, is actually a stationary equation. That means, it is actually a algebraic equation actually. and if you solve this algebraic equation, attempt to solve, then u becomes a function of x and lambda actually. Okay. So, for getting the solution from here, we really need to have an idea of both x as well as lambda. I mean, that is the difficulty actually. Okay. And third point, because the boundary conditions are split, it essentially leads to 2-point boundary value problem, and that is the point I have explained already. So, the problem is in 2n dimension, and n conditions are given at one point of time, which is initial time, and n more are given at the final time actually. So, that excites the case of 2-point boundary value problem, which are usually difficult to solve. And also remember, the state equation is given in this form where the initial condition is given. That means, the state equation develops forward in time, where the co-state equation, if you see, the boundary condition is at Tf and the equation is like that. So, it is actually backward in time. So, that is the state equation develops forward, whereas the co-state equation develops really backward actually. And traditionally, these 2-point boundary value problems demand computational intensive iterative numerical procedures, and some of that we will see in the next class. And the iterative numerical procedures, even if you do it, not only computational intensive, but essentially you are getting a solution for that particular initial condition ultimately. So, if your initial condition is changed somewhere else, then you have to really excite that solution loop one more time. In other words, because it is initial condition dependent, the solution is really not in closed loop actually. Okay. So, essentially what you are getting here is ultimately, even after this iterative numerical procedures, we are getting really an open loop solution actually, which is typically not good in practical implementation. And of course, there are ideas how to augment this controlled solution with a little deviation killing controller to make it operate on a closed loop actually. That is what we will probably see in next class actually. Now, before proceeding further, let us observe these couple of things. Okay. The first useful theorem is something like this, which tells us that the Hamiltonian H, if the Hamiltonian H is not an explicit function of time, then the Hamiltonian H is constant all along the optimal path actually. Okay. So, how do you do that? How do you prove? Let us is a very straightforward proof rather, which tells about, okay, if you take total derivative of Hamiltonian d by dt of H, there is nothing but partial derivative of that plus these terms actually. Okay. Right, the x dot transpose times del H by del x plus like u transpose and things like that actually. Okay. Right, and then what you can do here is you can combine these two terms, because del H by del lambda is nothing but x dot, this is one of the conditions, and then you can also excite this x transpose y equal y transpose x as a set of ideas there. So, using all that you will be able to combine these two terms actually. Okay. In other words, this term and this term, okay, can be combined and then written in that form actually. Okay. And remember, del H by del lambda equal to x dot is nothing but your state equation by x dot equal to f of t x c. So, while combining that, we have already used the state equation really. Now, after combining, you can also see that this particular thing satisfies co-state equation, because lambda dot is minus del H by del x, and del H by del u equal to 0 essentially satisfies the stationary equation or the optimal control equation really. So, using the state equation, co-state equation and optimal control equation, which are anyway true along the optimal path, we are left out with the fact that the total derivative of Hamiltonian is nothing but partial derivative of the Hamiltonian on the optimal path of course. And hence, if the Hamiltonian is not an explicit function of time, and most of the time it is so, because we selected that way, I mean the cost function is selected, but most of the time we talk about non-autonomous system and state equation also. So, the Hamiltonian really is not a function of time, then essentially what happens is the total derivative of Hamiltonian with respect to time is 0, and hence if H is not an explicit function of time, then this is true, and hence what you are telling is H needs to be constant along the optimal path actually. Okay. The only condition that is necessary is Hamiltonian should not be an explicit function of time, which is a free variable. Alright, so that is a useful theorem. Sometimes it helps us to validate our results, whatever results we get. If you claim that Hamiltonian is really not an explicit function of time, then probably you can evaluate these two derivatives. I mean this partial derivative Hamiltonian with respect to time, and you have to show that essentially that is 0 basically. Okay. So, this essentially is a useful theorem which helps us in validating sometimes validating our results. Sometimes it may also help us in finding out little new numerical efficiency, I mean numerically efficient I mean this computational procedure to solve these problems actually. Alright, so that is the theorem. Now, before proceeding further, we also notice that there is a general transversality condition or general boundary condition with T0 x0 fixed. If T0 x0 is not fixed, then also it is possible, and but here we are talking T0 x0 fixed. So, the general condition turns out to be something like this, okay, where this final time, variation of final time is also included actually. So, as a special case, if you see, if Tf is also fixed but Xf is free, which we have discussed just now, then obviously this Tf is fixed, so variation of Tf is not there. So, that means that is 0. So, you are left out with this coefficient equal to 0, and hence lambda f is equal to lambda at Tf, which is lambda f is equal to del phi by del x at Tf, which is already, which we have already seen actually. Okay. Now, what if Tf is free but Xf is fixed? Those that can also happen. Okay, that's a part of the problem formulation. Suppose you want to do that way, then the condition turns out that this is 0 anyway, because both x0 is fixed, there has been no variation on x0 anyway already, and xf is fixed. So, the variation of xf is also 0, delta xf is also 0. So, that part is also totally 0, and you are left out with only this term where delta tf is not 0. That means the coefficient has to be 0 actually. So, what you are telling is if Tf is free but Xf is fixed, that is kind of a hard constraint problem, then Hamiltonian at Tf has to be like this, del phi by del Tf actually. Okay. So, this is another boundary condition, because we need one more condition to proceed further, because Tf is actually a free variable now. So, this gives us kind of that one particular condition which will help us adjusting the Tf actually really. Alright, so this is all about transversality condition and all that. So, what is the summary? If you given a problem, you try to formulate a proper cost function, and you select Hamiltonian. Hamiltonian is that L plus lambda transpose F, and all these conditions are known to you. Okay, state equation, co-state equation, optimal control equation, as well as boundary condition, and all these things needs to be utilized for solving any particular problem actually. Okay. And let us say demonstrate our ideas using one or two example problems now. This will hopefully make our ideas clear actually. So, the first example is essentially a small problem, which is a classroom demonstrative sort of problem, which we now typically call as toy problems also many times. So, problem is like this: x1 dot and x2 dot is like this, x1 dot is x2 and x2 dot is minus x2 plus u. Okay, so, and the cost function that we need to optimize is something like this. So, J is like that, and then T0 is 0 and Tf is 2, that is what we select. I mean, if you select something else also these things should be possible to solve, and then we are putting that x1 of 0 and x2 0 is 0. That means, the initial condition for both states are 0 actually. So, what is the objective? How do you actually formulate this problem? Now, T0 is 0, Tf is 2 is kind of obvious, you can change it depending on control operation duration actually. Now, this is a typical initial condition, what you are assuming that the initial condition sense it starts from the origin. That means, if the origin is somewhere else, we will do the coordinate transfer to put the initial condition at 0 actually. So, that is also not a problem. Now, how these terms come? Because ultimately what we want is the solution should go to 5 and 2 as close to 5 and 2 as possible. That means, x1 of x1 at Tf should go as close to 5 as possible, and x2 of Tf should go as close to 2 as possible. That is why these are deviation terms, and that is what you are telling, that error square has to be minimum and this error square has to be minimum, and along the way I also want to make sure that the control effort is also minimum. So, that is how this u square term pops up here in the cost function actually. Okay. So, this is how we formulate the problem, and let us try to see the solution part of it actually. So, the first thing to start the solution process is defining the Hamiltonian. Okay. Let us see. Okay. So, if you define the Hamiltonian properly, I mean then the results are ready anyway. So, Hamiltonian definition is something like L plus lambda transpose F. So, L is like this U square by 2, which is coming from here, plus lambda transpose F means lambda 1 times F1, F1 is this one x 2, plus lambda 2 times F2, F2 is that one. Okay. So, lambda 1 times x 2 plus lambda 2 times F2 basically. So, that is how it is there. Now, state equation is already there with us. So, what we need to kind of find out is co-state and optimal control equations actually. So, the co-state equation tells us that lambda dot is equal to minus del s by del x. That means, lambda 1 dot is minus del s by del x 1 and lambda 2 dot is minus del s by del x 2. Now, here is the Hamiltonian. So, if you take partial derivative with respect to x 1, there is no x 1 anywhere. Okay. So, the partial derivative with respect to x 1 is 0. So, the lambda 1 dot is 0, and certainly lambda 1 is a constant actually. Now, similarly, lambda 2 dot is the minus del s by del x 2, and now x 2 terms are there here. So, first term is here. So, that will give us minus lambda 1, remember it is minus del s by del x 2, that is minus lambda 1, and here it is because of the minus sign is already there. So, if you take partial derivative with respect to and then change the sign, it will turn out to be plus lambda 2. So, what is happening here? Lambda 1 dot is 0 and lambda 2 dot is like this. Okay. Now, optimal control equation sense, you have this Hamiltonian here, del s by del u it needs to be equal to 0. So, H is like this. So, del s by del u is something like first term is u, remember the 2 u will cancel with 2. So, the first term is u, and then the second term is partial derivative with respect to u is lambda 2. So, u plus lambda 2 is equal to 0, and hence u equal to minus of lambda 2 basically. Okay. So, ultimately if we get lambda 2 somehow, then our optimal control solution is there with us actually. Okay. So, and we will see now that getting that lambda 2 solution is actually can be exhaustive actually. In other words, you may require lot of algebra to get this lambda 2 really. So, let us see that how do you do that, and boundary condition sense we already know the initial condition, that is the origin 0 0, but the final boundary condition at Tf equal to 2, remember Tf equal to 2 here, there is nothing but del phi by del xf, right. So, your phi term phi term is something like this. Okay. So, del phi by del x 1 actually turns out to be like that, x 1 f minus phi. So, x 1 of 2 minus phi. So, that means the lambda 1 of 2 needs to satisfy this equation, and lambda 2 of 2 needs to satisfy similar this equation actually. Okay. So, how do you do that? That is the question actually now. Now, remember if I put u equal to minus lambda 2 back here, okay, then I can think that okay, this x 1 dot x 2 dot along with lambda 1 dot lambda 2 dot form a complete set of differential equation. They are functions for themselves actually. So, that is what I do here by defining this new state vector z, which contains both states as well as co-state. Okay. So, the first n elements are states, the next elements are co-states, and as I told, if I substitute this equation back in here, I can actually see that this is a linear equation. Okay. And this is also a linear equation here. That is why these problems are kind of simpler, why we call them as toy problems anyway. So, this is actually the linear system of equation in x 1, x 2 and lambda 2, and here is a linear system both in lambda 1, lambda 2. So, I can actually put them together and then talk about this particular system z dot is a z where a is given like this. So, essentially I am left out with a set of differential equations that are linear, and I need to have this only solve this homogeneous differential equation. Okay. Z dot is z. That is what we need to solve actually. So, now, obviously what we have here is a linear homogeneous differential equation in state space form. So, the solution is obviously this way, z of t is actually e to the power a t times c. Now, typically when you study linear systems solution and all what we have seen before, if you know z0, z of t0, then the solution is c is also z of t0 or z0, and you are done actually. That's the solution. But unfortunately, we do not have that, because the lambda 1 0 and lambda 2 0 are not known to us. What is known to us is lambda 1 of 2 and lambda 2 of 2, which are like conditions at the final time. Okay. If everything were known at the initial time itself, then it could have been done by now really. Now, because of that, let us proceed what we can do here, but we have to use these conditions anyway. Okay. So, let us start using these conditions. First condition is that t equal to 0. These first two conditions x1 of 0 and x2 of 0 needs to be 0 0 actually. Okay. So, if I put that at t equal to 0, then e to the power a t is e to the power 0, which is identity, and hence z of t 0 or z of 0 is actually c, and z of 0 first two elements will contain 0 0 anyway. Okay. So, that 0 0 comes here, and the right hand side it is c vector, that means the first c1 c2 comes in the right hand side. So, this expression tells us that c1 and c2 needs to be both 0 as 0. Okay. So, this out of this flexibility that we had, C contained 4 dimensional vector, right, I mean that is c1, c2, c3, c4, and out of that we see that c1 and c2 are already 0 0. So, we are left out with c3 and c4 really. Okay. that way to find out for using using this condition. Okay, this lambda 1 of 2 and lambda 2 of 2, using that condition we need to find out actually. Okay. All right. So, what do we do now? Tf equal to 2, we put that condition, and then we go back to this solution what we had. So, we put x1 of 2, x2 of 2, and lambda 1 of 2 and lambda 2 of 2 is like this. So, we put that here, and now it is no more identity, it is e to the power 2a, because t is 2 really. So, but A matrix is something that is known to us. So, e to the power 2a can be evaluated, we have seen that before. Okay. So, if you evaluate this e to the power 2a, it turns out to be like this. Remember c1 c2 is already 0 0. So, I do not have to carry them, I just simply put that 0 0 and simplify the algebra already basically. So, I am left out with something like this. So, if you ignore this term in between, I mean this middle term, if you can ignore a little bit, see the first and last term. What you see here is this is a system of 4 equations with 4 unknowns. 2 unknowns are c3, c4, and 2 more unknowns are x1 to x2 of 2. So, it has 2 unknowns here and 2 unknowns there. So, it should be possible to solve, and these are all we are lucky because we have all these equations are linear equations anyway. So, how do we do that? We now have to solve this set of equations to get c3, c4, which is possible anyway. So, for solving that in a vector matrix sense, what you need to do is expand these equations, all these equations, and then rearrange these terms a little bit actually. Okay. So, once you do that, you can rewrite the same equation in this form, okay, where all these unknown variables are here in this vector actually. Okay. And hence, the solution of this vector is this one, which is inverse of this matrix times this vector, which is nothing but like that, right. So, ultimately we got what is c3 and c4 actually. c1 c2 is already 0 0 anyway. So, that is why the solution that we are looking for e to the power a t times c is now available, and because that is available, our lambda 2, that is our ultimate objective, okay, that is also available now. Okay. So, that is how we see the problem. So, this x1 of t, x2 of t, lambda 1 of t, lambda 2 of t are all given like that, where this e to the power a t can be evaluated because a is something that is known to us actually. And ultimately, the solution of optimal control turns out to be like that, where lambda 2 t is the last row of this equation actually. Okay. And remember, this was a very simple problem to start with, because we had a linear system of equations. We had almost, I mean, when x2 dot equation which is decoupled from x1, x1 dot was not a function of x1 itself, okay, and the cost function was a straightforward quadratic cost function. Okay. Even under those situations, we really had to do this much algebra to get some solution actually. okay, for the optimal control. So, that is the typical situation. I mean, even if you are able to solve a optimal control ultimately in the closed form, we have to do a longhand algebra to get there actually. But ultimately the solution is beautiful, because essentially you can do many things. Now, once the solution is ready, you can, let us say I can put some let us say I put some S1 here, S2 here to begin with, and resolve the solve the entire problem in terms of S1, S2. Then I can simply plug more I mean different values of S1 and S2 here, and then to see the solution. Solution is already there with us actually. Now, similarly, if I do not put the value 2 here, I simply talk TF now, retain the generality that way, and then ultimately I put TF equal to 2, 3, 5, whatever I can do, and I still keep on getting solutions directly basically. So, that is how after getting the solution, the optimal control solutions are typically very nice. Alright, so that is was first problem. Let us move on to the second problem actually. Okay. Here is another slightly difficult problem, and probably the dynamic sense it feels simpler, because this is the dynamics, x double dot is u, okay, whereas the dynamics there was something like this. So, in that dynamic sense it feels slightly simpler, but we will see why it is a little more complicated problem actually. And here we typically talk about double integrator problem as a benchmark problem, because several problems can be thought of as an approximation to this double integrator problem. For example, if you have a satellite attitude control problem in aerospace engineering, and probably you have linearized the attitude dynamics, that means you talk about theta double dot is equal to 1 by I times tau basically about each of those axes, principal axis basically. So, instead of this 1 by I times tau, that tau by I is something that I am defining as u, angular acceleration actually. So, using this dynamics I can actually design a u for controlling the satellite attitude, if I assume linearized dynamics, small deviation, angles and all that actually. So, that is kind of a practical relevance why this problem was why we are talking about this particular problem actually. So, the double integrator problem we can pictorially represent like this. I mean x2 dot integrated gets x2, and that is nothing but x1 dot, and then say one more time if you integrate you get x1, and typically the output y is also x1 actually. So, why this problem is slightly more complicated? Okay. Because we want to minimize the final time actually. We are not talking about a kind of a fixed final time, we are talking about some sort of a free final time, and we want to minimize that time which is not specified. This TF is not specified a priori, because we want, let us say if it is attitude maneuver, you want to go from one position to another position, we better go as soon as possible actually. Okay. So, that way we want to formulate a problem where not only the control magnitude is minimum, but the final time is also minimum. By the way, this control magnitude minimum is also a significant property of satellite control, because the control availability is limited there. Either you talk about RCS control or you talk about reaction wheel, things like that, the control amount is not infinite. I mean, you are kind of severely constrained by control availability. So, we want to minimize the control effort, and we want to do your job as quick as possible actually. Okay. So, that is why I have selected the cost function that way. So, what I told is that TF is unspecified, and the control variable what you are assuming here is unconstrained. That means there is no hard bound for the control magnitude actually. So, I mean still we are minimizing this cost function. So, that is indirect way of doing that using a soft constraint approach actually. So, that is what we are doing here. Okay. So, let us see how do we solve this. So, the dynamics that we are having is this x double dot is used, but the cost function that we are having is something like this, where I want to minimize my control effort throughout, as well as I want to minimize my final time actually. Okay, how do I solve this problem now? Now, solution, first of all we need to put this dynamics in state space form, because our entire thing we know it in state space form only. So, state space form of double integrator is very straightforward, it is something like that, x1 dot is x2 and x2 dot is u basically. So, we have again got a linear system of equation where we talk about A and B matrices are defined that way actually. And y is typically defined x1, suppose we take position or the angle value only, then y is actually something given like that, where c is like that. Typically it is not required here, because we are not talking about estimation design or output feedback control, things like that actually. Alright, so we have this thing, and let's say let's impose a boundary condition where you take initial perturbation or something like this, initial angle. For example, I have whatever is my desired position, I will take the torque that is 0 0, that's the reference point actually, and with respect to that my initial condition was perturbed, something like 10 degree deflection I mean deviation I had actually. So you can visualize this problem as something like rest to maneuver actually, because ultimately the velocity, initial velocity was 0, final velocity that you want is also 0. So initially the satellite was kind of stabilized at one angle, which is of course not the desired angle. You want to make it desired, okay, but at that point also you do not want velocity build up to happen actually. So it is like something called rest to maneuver in satellite attitude control problem. Initially it was rest, the final thing that you want is also rest, but at a different angular position actually. So these are the problem, that's the problem that we are talking in a linearized setting actually. Okay. Remember when you talk about the nonlinear system dynamics for the satellite attitude, it will have a additional component before you basically. Anyway, so this is how the problem formulation, this is A, B, C, and then these are the boundary conditions that we have. First thing to proceed further, even though we did not talk that in the previous example, is to have controllability check. Okay, that is the standard in any control design, because that is a great technique that we have for linear systems actually. And remember this is already an LTI system. So why not making use of that, which we know very clearly. So the controllability matrix is A and AB. So that is what it is, that is a controllability matrix. Obviously the determinant of this one is -1, which is not 0, and hence the system is certainly controllable actually. Okay. Now necessary condition of optimality, first thing is Hamiltonian. Hamiltonian is remember that half u square is coming from here, L plus lambda transpose F, F is that. So that is L plus lambda transpose F, okay, Ax plus Bu. So that the necessary conditions of optimality is essentially 3 path related things. One is state equation, optimal control equation, and co-state equation. So state equation already we know. Optimal control equation is del S by del U equal to 0. That means if you apply this one here, first term is U plus the second term is B transpose lambda from this term. So U plus B transpose lambda is 0. So U equal to minus B transpose lambda, or again if you do that B transpose, because B is in this form. Okay. So B transpose is 0 1 0 1 into lambda, that means it is essentially lambda 2. Okay. So again if you know lambda 2, the negative of that is your optimal control actually. On the co-state equation sense, it is lambda dot equal to minus del S by del X. Again you go back to this minus del S by del X, the first term will pop up from here, that is del S by del X, first term is A transpose lambda. So that is minus A transpose lambda, and there is nothing there actually anywhere else. So lambda dot is equal to minus A transpose lambda here. So that needs to be solved actually. And very clearly you can see this lambda dot turns out to be a kind of a homogeneous system. It does not depend on X in this particular problem actually. So how do you do that? Because lambda dot is A transpose lambda, it turns out to be like that, because A is also a simplified matrix now. So lambda 1 dot is 0 and lambda 2 dot is minus lambda 1. So because lambda 1 dot is 0, lambda 1 is constant C1. Now lambda 2 dot is minus lambda 1, that is minus C1, and hence lambda 2 is minus C1t plus C2 actually. Okay. So because the lambda 2 is like this, U equal to minus lambda 2, which is that way. Okay. But also remember C1 C2 is something that we have not got it yet, we have to find that out actually. Okay. Now optimal state solution, we will go back, because here we have utilized optimal control equation, okay, right, and in co-state equation as well actually. Okay. So state equation we will go back and then try to use this state equation what we had here, okay, sorry, this one, and then we because we already know this form now. Our state equation is x1 dot is x2 and x2 dot is u. So x1 dot is x2, so let us keep it that way, but x2 dot is u is nothing but this one. Okay. So we put it that way. Now because x2 dot is that, so x2 is obviously one integration, so that means this form actually C1 t square by 2 minus C2 t plus C3. Now we go back to that one and tell, okay, x1 dot is x2, so x2 is available to be in now this form. So x1 of t is nothing but integral of that particular function, and hence it turns out to be that way. So, you are essentially having C1, C2, C3, C4, which is makes sense because we have a 2 dimensional problem. X1 and X2, it's a, I mean in a state space it is 2 dimensional problem, but state and co-state space together we have a 4 dimensional problem, 2 n dimensional problem really. So, we have these 4 constants to find out actually. Now, this is where our boundary condition will help, and tell okay, x of 0 is there, 2 boundary condition, and x of TF is also there, 2 more boundary conditions. So, let's plug in those. Okay. All right. So, try to put it back, and then once you put x1 of 0 and x2 of 0, okay, x1 x2 like that. So, once you put 0 0, we are left out with C3 and C4, all of the terms are 0. That means C3 and C4 turns out to be 10 and 0, because that is what the initial condition given to you basically, okay, 10 and 0. So, C3 and C4 values we got already. Okay. So, after using these values, this x1 and x2 turns out to be like that, where C1 and C2 are still left out unknowns actually. Now, we will use the boundary condition at t equal to Tf. Okay. So, x1 of Tf is turns out to be like that, but the problem is here Tf is an unknown quantity. Okay. If it is known, then we could have actually kind of got the values and we could have got the values for C1, C2 actually. So, essentially we have 2 equations, but 3 variables C1, C2 and Tf as well. So, now how do you solve this? That is where we bring the other boundary condition and tell okay, del phi by del t at Tf has to be negative of Hamiltonian at Tf. So, if you put that condition back now, and then phi is an explicit function of Tf now, remember that, because that is what we have formulated, this is our phi. Okay. So, we put it back there and then tell okay, this is what kind of this is additional conditions. We put it back, this is 2 Tf and this is this side of the story. Now, we have everything known in terms of C1, C2, C3, C4 already we found out. So, we put it back every condition, okay, and then use whatever boundary condition you know, x2 of Tf is 0. So, then we are left out with something like that. Okay. So, this is one more equation that we need to satisfy. So, now we have got 2 equations from here and one more equation from here. So, put them together. Now, we visualize a system having 3 equations and 3 unknown quantities. So, okay, essentially we can solve for that, and preferably we need to solve it in closed form, that is what you are looking for. So, we can rush it to numerical algorithm like Newton-Raphson technique if nothing is feasible, and we can do that, but essentially we can think of solving it in a closed form way. The way to go is probably first 2 equations, if you observe these are linear equations in C1 and C2. So, you represent C1 and C2 in terms of Tf, from you solve for C1 C2 in terms of Tf, and then substitute for that here, and then you will get a bigger polynomial equation for in terms of Tf, and this polynomial equation you can try to factor out and try to solve it, discarding this kind of unwanted solution which are practically non-realistic. For example, if it turns out that Tf is less than equal to 0, certainly that is unrealistic, we can kind of discard that. So, that is the way to solve. So, ultimately we will be able to solve, and then we will tell okay, C1 C2 Tf is something like this in this particular problem, hence u is something like this, C1 T minus C2, which is like this. Ultimately we got what is our u, optimal control actually. So, finally you remember this is actually, even though we got the solution, we essentially landed with an open loop control, and the application of control has to be terminated at Tf, which is needs to be decided a priori. I mean beyond that the solution is not valid. You do not have to define Tf, because Tf is something that you are evaluating here, which is minimum Tf, but the control law is really not valid after that actually. Anyway, so this is where this is what I wanted to discuss here. We discussed about optimal control formulation, necessary conditions, as well as other things actually. Many things, the references are also given here. You can see some of these references to get more information from there actually. All right, thank you.